In this video, I'm going to work through an example showing you how to calculate an equilibrium constant from standard free energy data. So for this example, we're looking at the dimerization of NO2 gas into N2O4 gas. And as you can see, we have been given a balanced chemical equation for that process. And we've also been given the standard free energies of formation for both the reactants and the products. We've been asked to calculate the equilibrium constant. So if we go back to our equation map, we can see that we have been provided with standard free energy of formation data, and we are being asked about the equilibrium constant. And so our path from what we're given to what we're trying to find out is going to be going by way of the standard free energy change for that reaction. So we're going to have a two-step process here. Use the standard free energy of formation data to calculate the standard free energy change for the reaction, and then use the standard free energy change for the reaction in order to calculate the equilibrium constant. So for step 1, we know that the standard free energy change for the reaction is going to be equal to the standard free energy change of our product, which in this case is the N2O4 gas, minus the standard free energy of formation of our reactants, which in this case is our NO2 gas. And because we have the coefficient 2 in front of the NO2, we need to use its standard free energy of formation twice. So we plug in our numbers and we get 97.89 kilojoules per mole minus 2 times 51.31 kilojoules per mole. And that gives us a standard free energy change for this process of negative 4.73 kilojoules per mole, which means that under standard conditions, we would expect it to be favored in the forward direction. But that's not what we're being asked. We're being asked to calculate the equilibrium constant. So to calculate the equilibrium constant, we take out our delta G naught equals negative RT ln K formula, and we rearrange it as we did in the last video to give us the equilibrium constant equal to e to the negative standard free energy change for the reaction divided by ideal gas constant and also divided by temperature in Kelvin. Notice that we are operating at 25 degrees Celsius because if we weren't, we would have to apply correction factors that we haven't talked about yet. And that, as we will remember, is 298.15 Kelvin. So then we plug in our numbers and we get negative 4.73 kilojoules per mole divided by 8.314462 joules per mole Kelvin times 298.15 Kelvin. The kelvins cancel, the per moles cancel, and we need our joules and our kilojoules to cancel because we can't be left with the units in an exponent. That would just be a mess. So we need to include a conversion factor to convert the kilojoules into joules. And then our kilojoules cancel, and then our joules cancel. And when we throw all of that into a calculator, we get an equilibrium constant of 6.74. On the next page, we're asked a related question. Now we are asked if the reaction is spontaneous or thermodynamically favored in the forward direction, given specific pressures of each of the two gases. So we've been given activities of the two gases from which we can calculate the reaction quotient for the system under these conditions. So we will remind ourselves of what our equation is. It is 2NO2 gas in equilibrium with N2O4 gas. And we've been told that the pressure of the NO2 is 0.4 bars, and therefore the activity of the NO2 will be equal to 0.4 bars divided by 1 bar, or 0.4. Similarly, the activity of the N2O4 gas is going to be equal to 1.8 bar divided by 1 bar, and therefore the activity of the N2O4 is going to be equal to 1.8. Using those values, we can calculate a reaction quotient, which will be equal to the activity of our product, so activity of N2O4 gas, divided by the activity of our reactant, so that's NO2 gas, but because there's two of them, we have to square that, and so we get 1.8 divided by 0.4 squared, or 11. Now, on the previous page, we calculated that the equilibrium constant for this process was 6.74. And so we can determine whether this reaction is favored in the forward or reverse reaction by doing one of two things. We can either directly compare the reaction quotient to the equilibrium constant, or we could pick up our reaction quotient and combine it with our standard free energy change from the previous page and calculate an actual free energy change for the reaction, and then look at whether that is positive or negative. So in this case, we can see that the reaction quotient is larger than the equilibrium constant. 11 is bigger than 6.74. And therefore, the reaction is favored in the reverse direction. And therefore, it is not favored in the forward direction. So I personally think this is by far the easiest approach to this question, but you will find that in thermochemistry there are often multiple routes to the same place. And as I mentioned, we can take this reaction quotient and we can combine it with our standard free energy change for a reaction and use that to calculate an overall free energy change, and that will also answer the question just in a different way. So to do that, we need to remember that delta G naught is equal to negative 4.73 kilojoules per mole. We calculated that earlier. And the reaction quotient is equal to 11, but I'm keeping all the digits from my calculator. I'm not just typing in 1 starting fresh. Always retain all your digits. So I can take those values and I can combine them to calculate a free energy change for the reaction under these conditions. So delta G is equal to delta G naught plus RT ln Q. And I plug in my negative 4.73 kilojoules per mole here. And I plug in my 8.314462 joules per mole Kelvin here, times 1 kilojoule per 1,000 joules, so that I'm able to add up the two components of my answer, times 298.15 Kelvin, times the natural logarithm of 11. Which gives me negative 4.73 kilojoules per mole plus 6.00 kilojoules per mole. And therefore, under these conditions, the free energy change for this process is plus 1.27 kilojoules per mole, which is a positive value. And therefore, the reaction is not favored in the forward direction, but rather it is favored in the reverse direction. The exact same conclusion as